Hello, my name is Eitan Greenspoon. I'm a professor at Columbia Engineering, and I'd like to welcome you on a ride through animation and CGI motion. So let's dive right in. Computer graphics has come a long way. Today we can see beautifully rendered images on the big screen. We can see statues that are across the world, and we can see them at the level of individual chisel marks. And we can see buildings before they've even been built. Now, what all of these images have in common is that they're all frozen in time. And the topic of our course is going to be motion, depiction of motion, animating motion on the computer. But before we go there, let's have a little history of the depiction of motion. People have been interested in looking at motion and depicting motion for a very long time. For example, about 40,000 years ago, there were paintings drawn on the faces of caves. Here's one that was discovered in Spain, for example. And you might say, oh, that's just a painting of an 8-legged boar. But maybe not. Maybe that's a painting of a 4-legged boar with some interpretation of the motion of the legs. So people have been trying to find ways of describing how things are moving, even when they had to depict a single image. Here's a Persian vase, probably from a few thousand years ago, and the artist was telling a story, and we can see the story by unrolling the image of the vase, and here it is, and it's the story of a goat that's jumping up to eat a leaf. And so the idea here is that as you rotate the vase around, you kind of see this story of motion unfold in front of your eyes. And this idea of using rotation to show a sequence of images was taken to the next level in the 1800s with the invention of devices such as the praxinoscope, which had a series of mirrors and images. And as we looked at one fixed place, we saw many images flash in front of our eyes. And each image persisted for long enough that our brain interpreted this as an animation. Actually, the praxinoscope is the modern predecessor to, or is the predecessor to modern cinema. Here is the Théâtre Optique in Paris in 1892. And if you look closely at the image, you'll see a sequence of little mirrors on the rotating table. So it's just an oversized praxinoscope. And it was used to show some films, short films. In fact, here's one of the first ever film billboards, if not the first, for a movie playing at the Théâtre Optique. So this kind of gives us a story of the depiction of motion to modern times. And of course, when I think of animations, I don't know about you, but the first thing that comes to mind is some of the Disney animated movies, such as Snow White and the Seven Dwarfs. And what's interesting there is that artists had to mix storytelling with physicality. The actual physical behavior of materials was really reinforcing the storytelling, the bags moving, the beards moving, the hats moving. And so what I've put up here is one of the typical example exercises that is given to an artist, which is draw me a sack of flour that's angry or sad or sleepy, that has some emotional intent or some action, but at the same time retains its sack of floweriness, that is, its physicality, if you want. And so this mix between physics and storytelling has been an undercurrent of animation for quite a while. And as we think about what's going on here, we realize that to animate motion, we need to take into account behaviors such as gravity, air, flexibility, obstacles, and friction. And all of these come together to give a realistic depiction of motion. And these considerations are important not just for artistic storytelling, but for other very exciting applications. For example, if you open up a drawing program such as Adobe Photoshop or Adobe Illustrator, the underlying paint brushes are simulating the flexibility of bristles and the deposition of paint onto the canvas, or the flow of paint around the canvas, so that artists can make on the computer very realistic images by using physics-inspired tools. If you think about how fashion is evolving, there's a trend towards incorporation of computer-aided design of garments. And interactive garment design tools, such as this one here, allow the designer to modify a 2D pattern for the design of a garment while seeing a 3D preview of what the draped garment will look like. So in this way, they circumvent the long process of sketching out a pattern, cutting it out from fabric, sewing it together, and then putting it and pinning it on a mannequin, only to discover that the design is flawed or needs some changes. So to do this again, one needs to have understanding for the flexibility of the fabric, the stretching, the bending, all of the physical forces, contact and friction that come into play. Also, in robotics, an understanding of physical phenomena is critical. For example, if we want to have robots that can, I don't know, fold our laundry, for example, then they need to understand how the world around them reacts to manipulation. And once simulations exist that can teach a robot or help a robot to understand how the world around it will react to stimuli, then the robot can actually undertake these projects, and we can just, lay back and relax while the robot does its thing. Isn't life great? So those are kind of the application areas of simulation, and of course there's many others. And that's what we'll cover. We're going to cover the fundamentals of physical simulation, how to put classical mechanics, how to put physics into the computer. To do that, we're going to start by focusing each week on the smooth theory that defines the physical system. And then we're going to look at the corresponding discrete theory, that is, a theory that's inherently computable. And of course, once we have a discrete or computable theory, we're going to have to discuss numerical methods that are necessary to implement this on the computer. And then how do we get those computer algorithms to run efficiently, to run practically for large problems? So we're really going to focus on the fundamentals of running through a physical simulation on the computer. Now, we're not going to get a chance to look in depth at other artistic aspects of animation. For example, we won't have much control of, we won't have much of a look at emergent phenomena such as flocking or agent behavior, crowd behavior, or in general, we won't look at control of physical systems. We also won't look at rigging and interpolation, which are necessary for editing existing animations, or artistic direction. We're only going to give a light lip service to that, and keyframing. So for these topics, I'll ask you to turn elsewhere. So with all of this in mind, I'd like us to dive in and have a more in-depth, meaty look at those things that we will be covering.